Hello students, how are you? In the previous classes, we discussed covalent bond, valence bond theory and overlapping. But in today's class, most important topic of the chapter chemical bonding, that is hybridization. Students, hybridization is one of the most revolutionary concept given in the chemistry. The word hybridization is taken from the biological word which comes from the biology is hybrid. In the biology, there is a word hybrid. Hybrid means mixture. See, there was a question in front of us that how these covalent bonds form. In order to answer this question that how these covalent bonds are formed, we gave the concept valence bond theory. Primarily in the valence bond theory, we gave the concept of overlapping, and we said that overlapping is the mixing of orbitals, and because of the overlapping there is a formation of covalent bond. But later we came to know that concept of overlapping, I'm not saying that it is not correct, still it is correct, but later we came to know that concept of overlapping is not completely valid for multi-atomic species. Now see, those species who are diatomic. What do you mean by diatomic? Diatomic species like hydrogen, like nitrogen, like F2 and other. Concept of overlapping is sufficient enough to explain bonding. But what about polyatomic? In the polyatomic species, my dear students, in the polyatomic species like CH4, like SO2, like IF7, and like NH3, overlapping itself is not sufficient enough to explain bonding. Here, in order to explain the bond, we gave the another concept of called as hybridization. So hybridization we gave to explain the bonding, covalent bonding moreover between atoms. Now in this concept of hybridization, we say that before overlapping, orbitals mix with each other. When they mix with each other, they form new orbitals called as hybrid orbitals. So here we go with the concept of hybridization. So what is hybridization? It is intermixing of the atomic orbitals of comparable energy, means their energy should be nearly same. I'm not saying that it should be exactly same, but it should be nearly same. There should not be any huge difference between their energy. So atomic orbitals of the comparable energy of the atom, they form a new set of equivalent. The term equivalent is very important, means same. Hybrid atomic orbitals are called as hybridization, means when different orbitals participate. See, this is s orbital, this is p orbital. When they overlapped with each other, they formed this hybrid orbital. This one is the hybrid orbital. You see here in the hybrid orbital, prior to the hybridization, S was spherical, P was dumbbell shape. This is spherical and this is dumbbell shape. But after hybridization, this hybrid orbital is neither spherical nor dumbbell shape. It has some different shape, and all the hybrid orbitals will have exactly same shape. So these are some features of the hybridization. Number of atomic orbitals participate or they undergoing hybridization, they produce same number of hybrid orbitals, which means if in the hybridization 2 orbitals participate, then new hybrid orbitals formed will be 2 in number. If 3 participate, new will be 3 in number. If 5 will participate, new orbitals formed will be 5 in number. If 7 will participate, obviously there will be 7 in number. So another point is hybrid orbitals have same energies and shape. This was the need of hybridization. Before hybridization, orbitals have different energy. energy of 2s is different than energy of 2p. So they have different energy and of course shape. S is spherical, P is dumbbell, D is double dumbbell. So before hybridization, they have different shapes. But after hybridization, all the orbitals will be of same size, same shape, same energy. They are exactly identical to each other. They are exactly identical to each other. And this is the basic need of hybridization. Moreover, hybrid orbitals, they form more stable bonds. You must be thinking, why sir? Why they are forming more stable bonds? See, in the last class, I told you that stability of bond is directly proportional to the amount of overlapping. Greater the amount of overlapping, greater will be the strong bond between atoms. So hybrid orbitals, they do more overlapping than any other unhybrid orbital. So in case of hybridization, and when amount of overlapping is more, of course bonds will be more stable. And you know what these hybrid orbitals do? What they do exactly? These hybrid orbitals, they arrange themselves around the central atom and they occupy particular direction in the space to have the minimum repulsion. And during this attempt to minimize the repulsion, they attain a certain geometry. That is the reason why hybrid molecules are directional. They have some certain geometry. You must have heard the name tetrahedral, octahedral, triangular bipyramidal, trigonal planar. These are the geometry which are attained by the hybrid molecules. Let me tell you one more time, and why these geometries are attained. Because those orbitals which are hybrid orbitals, they arrange themselves around the central atom in such a way so that repulsion between them could be minimized. Because of this minimum repulsion, maximum stability, bond is formed. And like I said, because of these directional properties, a molecule acquire definite shape. So there is a definite shape of the molecule because of this directional property. Now you must be thinking that how many type of hybridization do exist. See students, hybridization is of different types. In today's class, I will tell you about the sp3 hybridization and moreover sp2 hybridization. Rest hybridization we shall discuss in the next session. But why I incorporated these three hybridization together in front of you? Because you see, in these hybridization, there is no involvement of d sub shell. These are the hybridization involving S and P only. This is the first type of hybridization, sp3. You know how it is formed? It is formed by one S and 3 p orbitals. We know that p orbitals are perpendicular. So if it is px, one is py, another is pz. So when these 3 p orbitals and one s orbital, when they will combine with each other and they will form 4 new hybrid orbitals of same shape, same size and same energy. These are 4 new sp3 hybrid orbitals. Now you can see, you can check that all these 4 orbitals are of same shape, same size, same energy. Similarly, in the sp2 hybridization, there is a participation of 1s and just 2p orbital, not 3, 2. So 3 orbitals participated here and there will be a formation of 3 new sp2 hybrid. These are 3 new sp2 hybrid orbital. What about this sp? In this, one s and one p, just one p, they overlap and they form 2 new sp hybrid orbital. So like I said in the previous slide, the number of atomic orbital undergoing hybridization produces same number of hybrid orbitals. Now you see, when 4 orbitals participated, they formed 4 new orbitals. When 3 participated, they formed 3 new orbitals. And when 2 participated, they formed 2 new hybrid orbitals. Like I said, hybrid orbitals have same energy and shape. You see, these 4 hybrid orbitals, they have exactly same shape. Please don't mind if it looks like that one of them is slightly larger than other, but believe me, all these 4 new hybrid orbitals are exactly same in shape, size and energy, and the same goes with sp2 and also sp hybridization. Moreover, we said hybrid orbitals around the central atom occupy a particular direction in the space to minimize the repulsion, and because of this they attain certain shape and geometry. This we will discuss now in the coming slides. Alright, so here is the first example is sp3 hybridization. What is sp3 hybridization, guys? In this hybridization, it occurs where the valence shell of the central atom has 1s and 3p orbitals available for hybridization, and shape which is attained in this hybridization is tetrahedral. So it is also called as tetrahedral hybridization. Let me ask you one question, students. Do you know what is the meaning of tetrahedral? Do you know where this word came from? The word hedron came from Greek mythology. Every country has its own mythology, like we Indians also do have our own mythology. So as per the Greek mythology, hedron means phase. Hedron means face. So when you say tetrahedral, means the structure having 4 faces. I'll explain you how in the coming slides. So methane, ethane, both are the organic molecules, both are the hydrocarbons. They have sp3 hybridization. So what happens in the sp3 hybridization? Like I draw in the previous slide also, 1s and 3p. Which one? px, py, pz, all of the p. P subshell has 3 orbitals, px, py and pz. So when all of them, px, py and pz, they combine with the s orbital and they form 4 new. These are 4 new sp3 hybrid orbitals. Now these sp3 hybrid orbitals will further participate in covalent bond formation by overlapping. Don't think that overlapping is over and overlapping is not a valid concept or it is not good. Overlapping still holds good even though we applied hybridization. But remember students, hybridization never form bond. Bond is never formed by the hybridization. Hybridization is just the preparation of bond formation. Like these orbitals, when they combined and they formed these 4 new orbitals, it is not hybridization, it was the preparation of hybridization. So like methane, this is the example of sp3 hybridization. What is the electronic configuration of methane in the ground state of carbon? Everybody knows that carbon is having atomic number 6. So the electronic configuration of carbon in ground state is 1s2 2s2 2p2, means this 2s will contain 2 electron and this 2p will contain 2 electron. This is the ground state electronic configuration of carbon. But what about the excited state? This is the excited state electronic configuration of carbon. in which this electron from 2s orbital is excited and come in 2p sub orbital. So this is the ground state. You see the picture you see here is the ground state of carbon, in which we cannot form 4 bonds. In the methane, carbon has to form 4 bonds, but in the ground state there are just 2 unpaired electrons. So this electron is excited in the higher energy level, and finally we got this distribution of electron. This is 2s and this is 2p. Now s and p, all of them have one unpaired electron. When they will combine with each other, students, they will form 4. How many orbitals participating? 4. 1, 2, 3, 4. So how many new will form? These are 4 new hybrid orbital. What is the difference? Before hybridization, one was spherical, one was dumbbell. Energy was nearly similar but not exactly similar. Now after hybridization, these all 4 orbitals which are formed here they are exactly identical to each other, and this is called as sp3 hybridization. Now these sp3 hybrid orbitals, they are directed in the space at an angle of 109 degree 5 minutes away from each other as per the VSEPR, and it gives tetrahedral structure, like I told you, in which 4 faces are there, tetrahedral. So these orbitals, when they overlap with the 1s orbital of hydrogen, they form 4 sigma bonds. Now these red color orbitals you see here, each red color orbital is sp3 hybrid, and now this sp3 hybrid overlap with the hydrogen and form sigma bond. So you know what happens when I teach hybridization to these students, they started believing on their own that now overlapping is not valid. We don't need overlapping now, but please do take note of that bonds are always formed by overlapping only. 100 years back from now, we used to form bond with the overlapping. In 2020, we formed the bond with the overlapping. And in 2021, we are forming bond with the help of overlapping. Even though if you compare with 100 years back, in 1920, 100 years from now, in 1920, we used to form bond with the overlapping. And in today also, we used to form bond with the overlapping. The only difference is, students, the only difference is, previously we say that bond is formed directly by overlapping. But now we say that bonds are formed by first hybridization and then overlapping. First of all, hybridization take place. After hybridization, overlapping take place. This is what we say now. All right, I hope you are getting it. The next example of sp3 hybridization is formation of ethane. Ethane is an organic molecule, hydrocarbon, having formula C2H6. In this, each carbon will have 4 hybridized sp3 orbitals. Out of these sp3 orbitals, 4 sp3 orbitals, more likely, 3 sp3 orbitals, one of each carbon, they overlap with the 1s of hydrogen like this. This is carbon. This is also carbon, and 3 orbitals of carbon overlap with the 1s of hydrogen. This is 1s of hydrogen, and they are forming sigma bond, right? But what about this one? What about this orbital of carbon? And what about this orbital of carbon? They will also overlap with each other. They will come close and they will overlap with each other, and this overlapping is a student's new type of overlapping. You are watching for the first time is sp3 overlapping. Why it is sp3 overlapping? Because this orbital is sp3 hybrid and this orbital is also sp3 hybrid. So when these two overlap with each other and form the sigma bond, this is called as sp3 overlapping. Now what happens in this overlapping? This is sp3 and this one is s. So this is sp3 s overlapping, but this one is sp3 overlapping, because here in this case sp3 orbital of one overlapped with a sp3 orbital of another carbon. Alright, I hope you are getting it. Now each carbon we have one CC sigma bond. This is sigma bond and it is result of sp3 overlapping. And this sigma bond, this sigma bond, this sigma bond, all of them, this one and this one, I draw any one of them, they are result of sp3 s overlapping. Now because of this, there is a formation of molecule C2H6 in which sigma bond is there between carbon and carbon and sigma bond is also there between carbon and hydrogen, but the course of origin of both the sigma bond is quite different. The middle sigma bond is formed by sp3 overlapping, while the sigma bond between carbon and hydrogen is formed by sp3 s overlapping. Another example we take here is ammonia. Ammonia is NH3 students. In the NH3, atomic configuration of nitrogen is 1s2 2s2 2p3. We can elaborate this 2p3 further into 2px1 2py1 and 2pz1, because when the condition is 2p3 they will be distributed like this. So 2p1 2px1 2py1 2pz1, this will be the distribution of electron. Now the excited state electronic configuration remain the same. There is no need of excitation, and excitation is also not possible here. Why it is not possible here? Because in ammonia 2s is there, 2p is there, but 2d do not exist. There is no existence of 2d, so there will not be any 2d. So where we will excite this electron? Nowhere. So it will remain here only. Alright. So here only 1s and 3p, they will hybridize to produce 4 sp3 hybrid orbitals. Now these 4 will participate. They will form 4 new sp3 hybrid, 4 new sp3 hybrid orbitals. Out of these 4 orbital, one will contain pair of electron like this one, and 3 will have single electron like all of them. The orbital in which pair of electron is there cannot further participate in bond because it is already paired, and the one who is already paired cannot be paired again. So this orbital in which one unpaired electron is there will remain there only, right? And rest 3 will participate in bond formation like this. This is the orbital of ammonia in which paired electron is there, and these 3 have 1 electron which will further participate in the bond formation with the hydrogen atom. When they will form bond with the hydrogen atom 1s, 1 electron is of carbon and 1 is of hydrogen. Same goes here and same goes here. And then there is a formation of this molecule. One more thing you have to take notice of that is we never consider lone pair in the consideration of shape. So shape of this molecule will be look like this. If you have a look, this is pyramidal. So the shape is pyramidal. According to the VSEPR theory, shape of this compound will be pyramidal. So ammonia in which sp3 hybridization is there is pyramidal in shape. So only 3 out of 4 sp3 hybrid orbital, they participate in sigma bond formation. Why one is not participating? Because it is already having a pair of electron. Students, the purpose of bond formation is pairing of electron. But if it is already paired, you cannot form a bond with this orbital. So in the ammonia, in the NH3, one lone pair which is already paired will not participate in sigma bond formation, and rest 3 in which one electron is there will further overlap with the hydrogen. And what kind of overlapping is this? This is sp3 and this is S. So this is an example of sp3 S overlapping. Not only this one also sp3 S overlapping, this one also sp3 S overlapping. So here we explained how the ammonia molecule is formed with the help of overlapping. Remaining example of the hybridization we shall discuss in the coming classes. Today we discussed about the features of hybridization and examples of hybridization. There are many more examples of hybridization that we will gonna study in the coming few lectures. Thank you so much for attending today's session. I hope you liked today's class. Keep coming and keep studying. Good luck.